Okay, so I'm going to try to go through as many of the multiple choice questions in your mock exam as possible. So let's start with question 10 because we did the first couple in class. So the first one, or number 10, says an acetate buffer solution is prepared by combining 50 milliliters of 0.2 molar acetic acid and 50 mils of 0.2 molar sodium acetate, a 5 milliliter sample of the 0.1 sodium hydroxide is added to the buffer solution. So we make a buffer and we're going to add a base to it, a strong base. All right, which of the following is correct? The correct pairing for the acetate species that's present in the greatest amount, and what should be happening to the pH of the solution after you add the base. All right, so the pKa of the acetic acid is 4.7. All right, so first of all, this is a buffer. So when we deal with buffers, we can look at the Henderson-Hasselbalch equation, and we know that the pH is equal to the pKa plus the log of the base over the weak acid. All right, so the thing about buffers is when you make them, usually what you want to do is you want to combine these in a 1-to-1 ratio, because then what ends up happening is if it's in a 1-to-1 ratio, you're taking the log of 1. Well, log of 1 is equal to 0. So really the pH is equal to the pKa when the weak acid and its conjugate base are equal to each other. So, and that's exactly what we did here. We did 50 mils of the 0.2 of acetic acid, 50 mils of the 0.2 of the acetate. So at that point, before I did anything else to it, the pH is equal to the pKa of the acetic acid. So the pH was equal to 4.7 before we added the base. So before we added the base, this acetic acid and the acetate were equal, pH was equal to this. But we added a strong base, we added hydroxide to it. So I'm adding hydroxide to the buffer. Well, in the buffer it has an acid and a base. The base will react to the acid, so acetic acid. All right, and then H goes to this, so we make water and acetate. All right, so this is the reaction that's going to happen when I add that strong base, and then what will end up happening is all of the hydroxide will get used up, because if I look, it says that I'm adding 5 milliliters of a 0.1 molar solution of this. So really I'm adding 0.005 liters times 0.1 moles. And that means that I'm adding 0.0005 moles of that. Well, for acetate, I definitely have more than that. I added 50 mils and it was a higher concentration. So that means that this was present in a greater amount, because I had 50 mils and it was 0.2. I added more, it was more concentrated. So it's going to use up 0.0005 moles of acetic acid. So after the reaction happens, I am going to get rid of 0.005 moles of acetic acid, and then I'm going to add 0.0005 moles of my acetate. So I'm going to have more acetate, less acetic acid. So the acetate species that's present in greater amounts, well, that would be the acetate, because I'm going to make some when I use up that acetic acid in this reaction. So I can eliminate these two right now. Then I have my pH. Well, my pH, I'm making a base here, so it should become a more basic pH, which means my pH should go up. So it should be greater than 4.7, which is D. All right, so let's look at another one. Let's look at 11. All right, so an 11, oops, Okay, and 11, the molecular formula and the molar mass of two straight chain carbons are listed above based on the information which compound has the higher boiling point. Okay, so it gives us the formulas, and it gives us the molar mass right here. So when I'm looking at this, I have a hydrocarbon. Well, all hydrocarbons, when it's just carbon and hydrogen, are going to exhibit LDF, and predominantly LDF, because it's mainly this long chain of CH bonds. So this is ethane right here. And then the other one would just be the continuous. It would just be 4 carbons in the middle instead. So these two molecules both exhibit London dispersion forces because they're nonpolar molecules. The only difference is their molar mass. So let's go through the options. This one says because it has more hydrogen atoms, resulting in more hydrogen bonding. No, because these hydrogens are not bonding to an O, N, or F, so you can't have hydrogen bonding. If you look at this one, it says C2H6 because its molecules are smaller. They can get closer to one another, resulting in smaller, stronger dispersion forces. When atoms can get closer together, you're going to see a stronger attraction. This is not necessarily what is happening here. And then C2H6, because its molecules are more polar, that's just not true. They're both the same kind of structures here, it's just one is bigger. So really, it's C4H10 because it has more electrons, which results in more temporary dipoles, so it's B. So really, we're looking at the mass here. The higher mass, when you have similar intermolecular forces, will result in more London dispersion forces because it has more electrons though. So we don't say it's because it's more massive, it's because it has more electrons, which is what we usually see when the mass is higher. All right, so let's look at this one. The first 5 ionization energies of a second period element are listed in the table above. Which of the following correctly identifies the element and best explains the data? So we've seen this a few times. Basically, it's the energy removed to, or put in to remove an electron. So this is how much energy for the first, the second, then the third, and then fourth, and so on. Well, really what you're doing is you're looking for the biggest jump. Well, we go from 800 to here, and then we go from here to 3,000. Here we go to 25,000, which is huge. So every time that we pull off electrons, it requires some energy, but it's going to require more energy to pull off core electrons. So what you need to do is you need to look for that big jump. What that indicates is that we can remove the first electron, the second, and the third just fine. But after that, we've probably hit a core electron. So really this element right here is probably in group 3A. So if it's in group 3A, it's probably boron. And then it says because it has 5 core valence electrons, or because it has 3 valence electrons. If it's in group 3A, it has 3 valence electrons. So it's this one. It's not because it has 5 core electrons. I think boron actually does not have 5 core electrons. If you go back and look at where it is on the periodic table, I think it has 5 electrons altogether, and then 2 of them are core, which means they're not in the outer energy level. So for boron, the outside energy level is 2. So there's 2 valence electrons, or I'm sorry, 3 valence electrons on that second energy level, and then once you get rid of those, then you have the electrons on the first energy level, and it's going to require a lot more energy to remove core electrons. All right, so number 13. The exothermic dissolution of magnesium hydroxide is represented by this. KSP is this. Which of the following changes will increase solubility? So how can we make this reaction go more towards my reactant side? So when I look at this, I can eliminate one choice right now, because if I add MgNO3, well, when this dissolves, I'm going to make this. and this. So what I'm doing is I'm adding more magnesium. Well, if I add more magnesium, that's going to shift back to the reactant side, so it's going to be less soluble. So compounds are typically less soluble in solutions that contain its own ions. So it can't be this. All right, so decrease the pH, increase, or add a base. Well, when I dissolve this, I'm making a base. Bases react to acids. So if I reacted it to an acid, I would get rid of this, and then it would shift back. Or I'm sorry, it would shift to replace it. So this is Le Chatelier's principle. Whatever's done must be undone. So if you remove the hydroxide, the reaction is going to shift to the product side to create that thing again. So if I put an acid in there, that's going to increase the solubility. So if I decrease the pH, which means add an acid, that'll happen. If I increase the pH, I'm adding a base. And really, this is the same thing. I'm adding a base. Ammonia is a base. So bases don't react to bases. All right, so number 14, we have a heating curve. And it says that segment T is greater than segment R. And really, if you remember, when you go through a phase change, your temperature is not changing. So right here, temperature is not changing at all. Here, temperature is not changing. So I go from a solid to a liquid to a gas. So if I were to look at that temperature change that's happening here and here, well, I would need, like if I wanted to know the amount of heat energy that goes into it or the change in temperature, what I would do is I would solve for MCAT, mass times C times delta T. Well, when I have a liquid, my specific heat capacity is different. So really, for this change in temperature to be steeper, the specific heat has to be less than that of the liquid. So if I have a specific heat capacity and it's lower, that means that it takes less energy to heat it up. My temperature change is going to be greater, so it should be A. So also, if you're trying to calculate Q here, make sure you use the right specific heat capacity. All right, so let's look at this one. I have a solution prepared by mixing this component and this component. We're mixing the same amounts on the basis of the information above, so the Ka's, which happens in the lowest concentration. Well, let's see what happens when I put this into water. I'm going to make sodium ions and also H2PO4s. And then for this one, when I split it up, I'm going to have 2 sodium ions and HPO4. All right, so I already know right off the bat that's probably not going to be sodium. Sodium is a spectator anyway here, so it's just going to kind of sit in the solution, and I've already released 3 ions in it, so it's probably not sodium. That's in its lowest concentration. So what I need to decide now is between these 3 choices, what should be the lowest? Well, when I put this into water, I'm going to make H plus and this. When I put this into water, I'm going to make this and this. Well, if I look at the Ka values, this one is smaller than this one, which means this one will produce more products. The bigger K is, the more products you produce. Okay, so this one produces less. Well, on the product side here, I've got PO4. Product side here, I've got this. So really the thing that should be in the least amount should be this phosphate ion right here. So D. Let's go to 16. All right, so a certain gas, XY, decomposes as represented on the equation above. A sample of each of the 3 gases is put into a previously evacuated container. The initial partial pressures are given below. Okay, so it's asking which side the reaction is going to shift to. Well, it gives you a partial pressure of everything. So these are initial partial pressures of everything. So I have products and reactants. Before anything happens, you should recognize that if you're given a partial pressure or concentration of every single component in your reaction, you really need to probably look at Q to decide where the reaction is going to shift. So Q, remember, is the same thing as K, except it's at any point of the reaction, not just equilibrium. So Q is equal to products, which is the partial pressure in this case, because we're going to be looking at Kp, partial pressure of X2, partial pressure of Y2, divided by the partial pressure of Xy squared. All right, so we have that. So what we're going to do now is we're going to plug everything in. So X2 is 0.2, Y2 is 2, and Xy is this. Okay, so let's go ahead. 0.2 times 2 would be 0.4. 0.01 times 0.01, or for multiplying decimals, we're going to get a bigger decimal, basically, more decimal places. So 0.0001. All right, I don't like this math right here. So what we're going to do is we're going to move the decimal point. Okay, so let's move this one first. 1, 2, 3, 4. Okay, so now I have 1. So I'm going to do the same thing here. I'm going to move it 4 times. 1, 2, 3, 4. So 4,000. 4,000 divided by 1 would just be 4,000. So Q, I don't have to move the decimal point back because I moved it the same amount of times. So Q is equal to this. So now I'm going to compare it to K. So Kp is equal to 230. Well, obviously Q is bigger. Okay, so if you want, you can remember the trick. Q always shifts towards K. So if Q is above K, it's going to shift to it's pointing towards the left-hand side, so it's going to shift to the reactant side. You could also think about it this way. Okay, obviously this number is too big if it's greater than Kp, which means that we need to get rid of our products and make more reactants. So we're going to shift to the reactant side. All right, so looking at this problem right here, you have a reaction. You're adding lithium to water, and it tells you you're going to make hydrogen gas. Well, whenever you do this, whenever you add an alkali metal to water, you're also going to make a metal hydroxide. So you're going to make lithium hydroxide. All right, so now that we have our reaction, basically it said that we titrated this afterwards. So basically we took this substance, we made this substance, and then we titrated it with an acid. All right, so which of the following will most likely lead to an increase in the rate of reaction? So if I were you, before I even really read this, I would read the question first, then go back and look to see what information you need to pull from that. All right, so using 125 milliliters of water instead of 100, that's not going to increase the reaction rate. Water is already in excess here, so adding more is not really going to make the reaction go faster. Now, using less lithium, that's definitely not going to increase the reaction rate. We need to have more collisions. Using a 0.35 gram sample of lithium cut into small strips, that would definitely increase the rate. If I increase the surface area, I'm going to increase my rate of reaction. Now, if I decrease the water temperature, technically nothing was stated about delta H here, so it's probably not that choice. All right, so what will be the effect of the amount of gas produced if I use potassium instead? Well, if I use potassium, it'll be the same reaction, but the difference is potassium and lithium weigh different amounts with their molar masses. So whenever we're doing stoichiometry and we want to know how much gas is going to be produced, because that's what it's asking you. Okay, Zeus. Psst. Stop. Just stop. Sit down. Okay, whenever we do this, we need to look at the number of moles. So if I go pull the molar masses, 1 mole is equal to 39 grams here and 7 grams here. I have a lot more moles of lithium than I do of potassium, which means I'm going to end up getting more moles of hydrogen and more grams of hydrogen at the end. So it would be that, well, no gas will be produced. That's not true. We're still making hydrogen. Some gas will be produced and be less than the amount. That's true. Equal quantities, that's not true. We don't have the same number of moles. We have the same number of grams. And that's definitely not true. All right, so on the basis of the pH curve, the pKa value of the acid is closest to, all right, so when we're talking about pH curves and pKa, what you need to know is, okay, we have a halfway equivalence point, and then that is when the moles of whatever we're adding is equal to the moles of whatever we're reacting it to, okay? Now, the halfway equivalence point is the buffering region because that's when the weak acid is equal to the conjugate base, okay? What you also need to know is, at that point, that halfway equivalence point, the moles of the weak acid will be equal to the moles of the conjugate base, which means the pH is equal to the pKa here. So if I go look at the graph, it should be about 5. So the pKa value is about 5 here. All right, so now let's look at a net ionic reaction. Well, what you need to do is you need to look at the reaction overall. And remember, anything that's aqueous gets pulled apart, anything that's solid or liquid does not, or even a gas. So only aqueous things get pulled apart. So plus water as a liquid produces H2 gas and lithium hydroxide. So we're only going to split up things that are in the aqueous. So this is solid, this is liquid, this is gas. We can only split up this one thing, which also means we can't pull anything out of our net ionic reaction. So when we split this up, we're going to have two lithiums, and then 2 hydroxides. Like that. So it should be choice A. Oh, wait, I'm sorry. B. Okay, so in net ionic reactions, go through anything that's aqueous, pull it apart. If they could appear on both sides the same exact way, then cancel them. Lithium here is not the same thing as lithium here. It's a different thing. It's an ion here, solid there. All right, so let's look at question 21. Question 21, we have a benzene ring, and it wants you to, which of the following best describes the intermolecular forces of attraction between water and benzene? Best thing to do, let's start looking at the choices and see if we can eliminate anything. This one says the H atoms in benzene form hydrogen bonds between the O's and the atoms. This can't form a hydrogen bond because the H needs to be directly bonded to an O, N, or F, so it can't be that. Benzene is hydrophobic, and therefore its net repulsion, there is a net repulsion between water and benzene, and that is true, but that probably doesn't really answer the question that they're asking, because they're asking about the intermolecular forces themselves. So we'll leave it open for now, but let's see if there's a better option. It says there are dipole-induced dipole and London dispersion interactions between the water and the benzene. And then if I look at the other option, it says benzene is nonpolar, which is true. Therefore, there are no forces between water and benzene. That's not true, because everything has LDF. Everything. So there will be some interactions and some forces. They're not going to be very strong, but there will be some forces, and they still do end up repelling each other. If I put benzene and water together, they'll separate and sit in layers. But to say that there are no forces at all, that's probably not going to be the answer. Okay, so they're a dipole-induced dipole. So basically, water has a dipole, and it can induce a dipole in something that's nonpolar, like this. So that's true. And then London dispersion, everything has London dispersion, so this is our best bet. All right, so we look at this question. It gives us two solutions and the Ka values. It says, which of the following is true statement about the pH at the equivalence point? Okay, so if I look, it says that it has the same amount of each thing in the same concentration. Okay, so 20 milliliter sample of 0.1 of each of these things is titrated with 20 milliliters of 0.1 molar solution of sodium hydroxide. So they're at the same amount. They start with the same number of moles. But remember, whenever I take an acid and I put it into water, the Ka value tells you how much it ionizes. So how much does this reaction happen with water? So I'm making hydronium and acetate here. And for this one, it would be the same reaction. All right, so the Ka value tells you how much, to what extent this reaction happens. The pH is determined by the amount of hydronium that you make in your solution. So really, when you make a solution that has the same amount of both acids to start off with, the Ka values are different. So this one is 1, which means that I should have a lot more hydronium compared to this one, which has a Ka value less than 1. So just because I start off with the same amount of acid doesn't mean I'm going to end up with the same amount of hydronium. So this means that the pH of this acid should be less, or I'm sorry, not less. The pH should actually be greater than this one. Because remember, a pH is determined by the amount of hydronium. The less the pH is, the more hydronium you have. Okay, so this one is more acidic. So let's see if we can eliminate some choices here based on knowing that alone. All right, so solution 1 has a higher pH. Okay, we do know that should be true. So solution 1 has a higher pH. Solution 1 has a lower pH. Okay, so it can't be that one, because we know that the solution 2 should have the lower pH. It has a stronger acid, which means it has more hydronium, which leads to a lower pH. So it can't be these two. All right, so let's see which one it could be. Well, it says because this is a stronger acid. Well, if I look at the Ka values, this is the stronger acid, so that's not true. So, and then this one says that CH3CO2 has the stronger conjugate base, and that is true. So if I have a weak acid on this side, technically its base is stronger than the acid that you started off with. But just based on elimination there, you know that it has to be B, even if you don't understand that part. All right, so now let's look at 23. All right, 23 is a calorimetry problem. You're burning a cashew and you're also burning a marshmallow, and it wants you to compare the amounts of energy. So when I look at this, let's pull out the information first and let's just see if we can kind of reason our way through it. We have a cashew and we have a marshmallow. Well, let's figure out how much heat energy was released when this happened. So we have a can of water over it. We're allowing the energy to go to the can, and we're measuring the heat in the water. So heat is equal to the mass of the water for this one, times the specific heat of the water, times the change in temperature, which is 5. All right, so same thing down here. The heat is equal to, well, we have 2,000 grams of water here. And specific heat is the same, and the temperature change is also the same. So when I look at this, well, it looks like I'm going to release twice as much energy here. But if I go back, my cashew was only 1 gram, and my marshmallow was 3 grams. So what I need to do is, okay, if I do this, multiply this out, I get 21,000. And for this one, I'm going to get twice as much, so I'm going to get 42,000. So I went ahead and I did the math on this one, and I know it's got to be twice as much because my mass here is twice as much. All right, so, well, this is only 1 gram of cashew. This was 3 grams. So if we divide that by 1, it's still 21,000. If I divide this one by 3, however, I don't get 21,000. I'm going to get something that's actually less than that. 42 divided by 3 is 14. Plus 3 extra zeros is 14,000, which is less than the 21,000. So my answer should be C. The combustion of 1 gram of cashew releases more energy than 1 gram of marshmallow. So you have to really watch the information they're giving you. And if it had been the same amount of marshmallow, then the answer would be different. So watch that. All right, so let's look at this one. We have a particle diagram. It says that, well, let's read the question. Which of the following statement correctly predicts the change in pressure as a reaction goes to completion? At constant temperature, so temperature is not affecting it. And it also tells me in here I have a rigid reaction vessel, so volume is not changing. So the reaction is happening, and what's going to happen to the pressure? Well, there's a couple things that pressure depends on. Volume, which isn't changing, temperature, which isn't changing, and the number of moles. So if you look at PV equals nRT, those are the things that usually impact pressure here. So here I have 12 molecules, and here I have 8. I have less molecules, so I have less collisions, so my pressure is probably going to be less. So it's going to be choice B. The pressure will decrease because there are fewer molecules of product and then reactants. All right, let's look at 25. All right, so we have a reaction. Okay, it says, without even reading any of this, which of the following identifies the element being oxidized and reduced? Okay, so I need you to assign oxidation numbers. Okay, this is one of those weird rules. It's not a normal thing. Oxygen is normally -2, except if it's in a peroxide, it's -1. So that's one of those weird things. Probably won't see it, but just in case. Okay, so assign oxidation numbers. This is -1. Hydrogen's +1. Okay, well over here oxygen is 0. And then over here, because water is oxygen's no longer in the peroxide, it's -2, and hydrogen's still +1. Okay, so it's another weird thing because oxygen is going up to 0, and it's also going down to -2. So oxygen is oxidized and Oh, I'm sorry, not that choice. Oxygen is both oxidized and reduced. Okay. All right, so the O2 produced in the decomposition from 1 liter is collected and put into a 10-liter container at 300 Kelvin. What's the approximate pressure at 400 seconds? Okay, so we're looking at this data right here. For estimation purposes, assume that 1 mole of gas in a 1 liter container exerts 20 atmospheres of pressure. Okay, well, that's good to know. So let's look. Oops. All right, so when I look at that one, okay, so at 400 seconds, after 400 seconds, my concentration of H2O2 has gone down from 2.7 to 1.7. So it looks like after 400 seconds, 1 mole of H2O has decomposed. Because this is 1 mole per liter, and this is a 1 liter container. All right, so if I look at this, the only thing that's going to give pressure is O2. So if 1 mole of H2O2 is released, how many moles of O2 do I have? 1 mole of O2 for every 2 moles of this. So I have a half a mole of gas in that container after 400 seconds. So now I need to look at the other information that's given to me. It says that I started in a 1 liter container, I'm moving it to a 10 liter container. So my volume starts at 1 liter, it moves to 10 liters, and I know I have 0.5 moles of gas here. And it says my pressure at 1 mole, for 1 mole of a gas, is 24 atmospheres at 1 liter. Well, I increased my volume, so that means I'm going to decrease my pressure. If I increased my volume by 10, I should decrease this by 10 as well, so it should go down to 2.4 atmospheres. But that's for 1 mole of a gas. And I only have half a mole, so that should be half of that, so that's going to be choice A. All right, so which of the following statements is a correct interpretation of the data regarding how the order of the reaction can be determined? You know what, let's see if we can eliminate any choices. The reaction must be first order because there is only 1 reactant species. That's not true. That's not how it really works. So you can have 1 reactant, but it still might require it might still have the involvement of 2 molecules. So it can't be that it's just first order. You can't determine that. The reaction is first order if the plot of the ln of the concentration versus time is straight line. That's a true statement. So let's see if anything else can be eliminated. The reaction is first order if the plot 1 over the concentration versus time is a straight line. That's not true. That would be a second order reaction. And the reaction is second order because 2 is the coefficient of H2O. Well, what's the mechanism? Does it just happen in 1 step, or does it happen in multiple steps? Because if that's the slow step, then yeah, that's true, but that may or may not be true. Because we don't know the mechanism, we don't know the rate determining step. So based on that, I would pick that, just not even looking at the data. But let's and technically, with this being a multiple choice question, I mean, you could go through and you could actually graph this to see what you're going to get. But because it's multiple choice, you're not going to be able to do that. So this is the route I would actually take. I would go through, eliminate my choices. Okay, so 28, the reaction is thermodynamically favorable. The signs of delta G and delta S should be what? Okay, so if it's favorable, you know that it has to be spontaneous, which means delta G has to be negative, so it can't be this, it can't be that. So delta S, should it be positive or negative? Well, let's look. Well, right off the bat, I can tell I am making more molecules. I'm also making a gas from this, which is going to create more disorder. So it should be that we're getting a positive delta S here. So that choice is eliminated, that choice is eliminated. It should be B.